A manager of the data engineering team at Torc Robotics, and I'm here to talk to you about some of the lessons that we learned when building a data lake primarily on S3. If you don't know about Torc Robotics was founded in 2005. It was acquired by Daimler Trucks Auto Group in 2019, and since then has been laser focused on developing an L4 autonomous truck solution. The key reasons there, one is to support the US economy, delivering critical goods. Most of the things around you and that you're wearing, if you bought them in the US, were delivered by a truck. We want to reduce the environmental impact of shipping those goods. So 29% of the US greenhouse gases are emitted by transportation. So automated trucks can optimize for fuel efficiency, and you can run the trucks longer per day than with human drivers. So you get more goods moved per mile with less materials. And probably most importantly, improving safety. There are 415,000 truck crashes per year, and while that's lower than the number of car crashes per year and the fatalities involved are lower, the fatality rates are more than 10 times higher. But we're here to talk about S3 and how we use that. So I mentioned I'm part of the data engineering team, and we don't make the algorithms that go on the vehicle that decide when to change lanes or when to speed up and slow down. We don't determine which sensors go on the truck. We don't define the operating model, and we don't write the simulation. So, how do we help that laser-focused mission? For us, that's enabling the teams that do all those things by providing them the data, making it available quickly, reliably, scalably, cost efficiently, and from that perspective, I kind of wanted to describe what does our data look like, so you get a sense of what is our data lake. Our trucks collect multiple terabytes of data per hour, and we're in a mode where we're collecting all that data, although it's kind of an R&D mode, and the teams really need all the data at the moment. So we have data recorded in binary compressed format. Doesn't lend itself super well to data lakes. 99.8% of the data are images and point clouds, so there's a lot of media files. And then some of the data needs to be kept forever. I think the point here is that we have variable retention policies. We also have multiple access patterns. So I mentioned a lot of different use cases and teams. We have like a forensics team that would look into an incident that happened with a truck. Why was there a disengagement, or why was there some incident that happened? Why did the truck behave the way it did? Fleet ops and reporting. So if we want to know how many miles did we go, how many disengagements did we have, on which stretches of road, are we doing better over time, et cetera. Algorithm KPIs. So teams that do algorithms like deciding when to change lanes, are they doing better over time as they make changes? Machine learning training data. So we have to be able to help facilitate building those training sets for neural networks to recognize objects. And then finally, lots of ad hoc querying, so people need to know, what's in here? What can I use? So the first step we needed to do was make sure that we got all the data into S3. So we chose to work with AWS for the community support and the enterprise support. So we migrated all the data that we had on-prem, and we started collecting data directly from the vehicles into S3. And we built a data lake for probably the same reasons that a lot of customers would build a data lake. We wanted a centralized catalog for our disparate sources of data. So we have like our on-vehicle data, we have simulation collected data, data from all of our internal tools, weather and traffic data that come from external sources. We need that centralized access governance, and we wanted to have the integration with the different processing, analysis, and dashboarding tools like Glue, Spark, Athena, Jupyter Notebooks, SageMaker, QuickSight, Tableau, those kind of tools. So I mentioned the media problem. We have 99.8% of our total volume, which is many petabytes now, is media. And a data lake is really tabular data. So what did we do? The first thing that we did was we separated the media and the tabular data. So we have a process that takes that raw binary compressed data, unpacks it, and splits it up. So we can build a data lake on the tabular part. So one of the things that Christoph was talking about was intelligent tiering. We have a lot of things to do. We have a lot of ground to cover. We don't have a very big team. We do have, as the blue line on the chart on the left indicates, a variable retrieval rate. And our red line there is the total storage, and this is one particular bucket, increases steadily over time. The point is, using intelligent tiering is the graph on the right, that as the size continues to increase, our cost is growing in a gap. So like our size is outpacing our cost because we're using intelligent tiering. There's a little bump. It's a little confounded because we've changed some of our access patterns. And I'm going to talk about one of the reasons for why there's a little bump there. It gets close, but then you can see the gap widening again. One thing that we did, and Christoph was just talking about this, was the design of prefixes. So we did a pretty good job initially of when we were uploading the data about using a UUID to indicate different tests to spread out those prefixes. That's right at the beginning. But then when we started to unpack the media files, we didn't do a great job. So we have the test UID at first, but if you can imagine, you're unpacking data as a truck comes back in, has a lot of data, you start to unpack it. For certain sensors that have a high frequency, suddenly you're spraying a lot of data right at a particular key. And we found that our put object costs accounted for 8% of our total S3 cost. So that's kind of, we don't want to be spending our money there. We have petabytes of data. Seems a little bit useless. So one of the things that we did was something pretty simple. We just bundled the media files into tar files. So take 1 second of those media files and bundle them together. That comes with a little bit of a cost to package them up in the first place, and a little bit of a cost on when you're retrieving it. But very often people will retrieve bundles of the data. They don't want individual, one camera frame from one particular camera at a time is not always useful. But that did reduce our puts by 99% and eliminated the throttling that we had on the keys. I'm sorry, on the prefixes. The other thing about building a data lake, we do use a lot of Amazon Athena. So we had the option of going with something like Redshift, but Redshift has comparatively a pretty high cost, and we do have quite a bit of data. And I think most customers will tell you, you can't go wrong by using Redshift, and that's true, but we wanted to see if we can do that even less expensively. There's a lot of the data. We had no idea how long people are going to be accessing data after the fact. So we took a look at our Athena query performance, and if you're curious about how that looks for us, going directly to S3. We do pay attention to the S3 prefixes, and we designed how we created those prefixes based on the most common query conditions. And something that kind of goes overlooked is you should be setting partition indexes, because we've observed that the query times can improve up to 40% by setting partition indexes. So just designing those partitions and setting the indexes will really improve performance. And what we see for queries like that is very often less than 20-second query times. That's probably not great for certain user interactive applications, but for many of the analysis applications that we do where time is not so sensitive, that's actually quite good. And you can get longer, so we observe 1 to 12-minute query times for common full table operations. And skipping down to the bottom row, we do have tables with hundreds of billions of rows in them. So even that is actually pretty impressive. And complex queries can go longer. Athena's timeout is 30 minutes. We have definitely seen timeouts on some operations that are really complex. But I think the point is, in comparison to Redshift, I should go back for a second. In comparison to Redshift, we're not paying much for the data that we're not accessing. So when it's stored in S3, we're not paying for it to just sit there and not get used. And then finally, one of the things that we care about for query performance is server-side encryption. So we want to be able to store the data securely. It should be encrypted at rest. And we took a look. We wanted to see, does server-side encryption have some performance impact when you're using Athena? And we did a comparison, and there was no impact, which was really impressive. As a matter of fact, in some of the lines, you could see it's actually a little bit faster. I don't know. I'll have to talk to these guys and find out what magic went into that. But I think the main takeaway for us was that S3 does take care of a lot of the performance issues and cost optimization so that we can focus on the capabilities that we can provide to those other teams that get the trucks on the road. And we don't spend our time down under the hood and trying to optimize wherever we really need to.